Okay, good afternoon. I cannot see any of you from here, so I'm just looking at the light now. So my name is Anh. So MC is not mistaken, I flew all the way here from Singapore. And I work in a group at the university, at the National University of Singapore, and we develop a distributed deep learning platform called Apache Singa. And today I'm going to share with you all the lessons that we have learned during that process. So this is where I'm from, National University of Singapore, very beautiful campus at a very small island. Here's my group on a boat, but we don't work on a boat. This is some of our time off. And this word cloud here is just to show you that what we mainly work at. And our expertise, our background is on data management. We have a lot of projects on databases and distributed databases. And since last year, we have embarked upon a project on developing an open source distributed deep learning platform, because there was a lot of different tools for doing deep learning, but let me see how to do this. Okay, so there was a lot of like single node open source software for doing deep learning, but there's still a space for a distributed deep learning platform that can run across many nodes on the clusters. Okay, so we would like to be one of the first ones to have a crack at that space, right? So, but now, fast forward just 1 year later, you can see a lot of development on the deep learning space. And Google, Facebook, and Microsoft are the big players in that space. You can see on the left, there's a lot of headlines on deep learning, where there's one company release one technique and another company would try to match it with another release as well. And there are parallel development in the hardware community to come up with better hardware, better acceleration, just specifically designed for the deep learning. And so those are the news that you can see on deep learning that can be tagged under deep learning. And on the right, you can see a lot of articles, similar article, but on a completely different topic, which is on databases. And today, you already heard a lot of speakers speaking about their in-memory databases like Redis and Couchbase. And so, so the database community has been around forever, like from the 60s or from the 70s. And today, they are still very active communities. There's still a lot of commercial and a lot of big companies doing databases. So you can see that Cloudera is a big player. Amazon is also offer a lot of have a lot of packages for databases and graph databases. Google Cloud Data Flows and React as well is a latest development on the Internet of Things space on databases. Okay, so. So these are the summaries of all the buzzwords, as you can see when you read the articles, those articles. So me personally, if you asked me a year and a half ago, I would not be able to pass any of this word on the top part. Okay, so most of these are very difficult to understand if you don't have a background on machine learning or a background on deep learning. Right? So on the top, you can see something like convolutional neural net, backpropagation, autoencoder, downpour, sequence to sequence, data parallelisms. Okay. So those are the buzzwords that you can see now when you read articles under deep learning. And at the bottom, you can see an equally confusing set of words if you read articles about database themselves. Right? So there are something like distributed transactions, write-ahead logging, data integration. Well, actually, data integration is pretty straightforward. data flow processing, in-memory processing, command logging, query optimization, crowdsourcing. But okay, so those would be very confusing to people who don't work in the database bit or who don't have to manage a very big and distributed database systems. Okay, so the purpose of this talk is not to draw the line between those two set of words, but I try to bring to you some sense of how these two set of words are actually have a lot of commons. Okay, so this line there is just imaginary. We hope to be able to borrow many of the technique from the bottom half to benefit the top half as well. So there is actually the successful deep learning system has turned a few heads for people who are working on other fields in academia, like databases, distributed system, and security. So, so when you get a lot of attention from academia, you expect to be improved. I mean, the performance would be improved a lot, and there should be a lot of, so deep learning should expect to, to benefit a lot from those attention from the academia. Okay, so this is the agenda of the talk. First, I will go briefly over the deep learning background and talk about how database techniques could help improve deep learning, and at the other hand, how deep learning could also benefit database applications. And I will close with some word of our platform called Singa. Okay? So deep learning is just a special branch of machine learning that it can learn features to many layers. So from the very high level point of view, from a system level point of view, you can see the deep learning process as an iterative process. That the first step you do is to initialize a set of parameters. Like you have a black box, and in that box there's a lot of parameters you have to tune. And at first you have a very rough black box that doesn't do anything. And then you feed that black box into an iterative process, and at the end of the day, you hope to get back a very clever black box, even though, I mean, you don't understand much about what's going on, but from the performance, you can see the black box is better. So the first step after you initialize the parameters is to read the data in, and because the data is very big, in order of terabyte or petabyte of data, so you cannot read all in memory at once. So the way you do it is to break it down to mini batch, normally in megabytes, in 10 of megabytes, and then you compute, you run some algorithm on that mini batch, and then you update the parameter on that black box. Okay, so that black box keep getting refined every time that you run that mini batch computation, and then you repeat. Normally you repeat for days. Okay, so deep learning is effective if you believe what the newspaper tell you and you believe what all this previous speaker has spoken. Deep learning is very effective. It has found many applications in wide range of domains, not only image but speech recognition and natural language processing as well. And deep learning is big. I mean, it's not big in terms of money, in terms of market, but big in terms of the training time, in terms of the computational resource that it needs.
Let me help you with the microphone.
Okay, thank you. Okay. So the typical training time of a deep learning model is in order of weeks, right? If you have a lot of data and you want to increase or increase accuracy, then you normally have to train it in order of days and weeks. Okay, and finally, deep learning is difficult. Let's just say that even at the end, you come up with very accurate box that can predict 99% of the time. Just can predict right 99% of the time, but it's still very difficult to understand, and it's very difficult to tune, and it's very difficult to optimize as well. The fact that deep learning is very difficult that gives rise to the misconception that if deep learning one day, if a deep learning model one day could replace some human tasks, then I mean humans just have no idea how they do it, and humans just lose out on that task. Right? So today I will focus on the second part on how to scale the deep learning model that reduce the difficulty of training the deep learning, or to reduce the time of training the deep learning model. Okay. So the database community, they have worked a lot on distributed computations. Okay, you might not see it in products, but you might have heard that most of the tasks today are not running on single machine, but a lot of machine on a cluster, and most of them are commodity cluster. Right? So the database has tremendous amount of work on how to partition the data in a large amount of machines, and how to run the computation correctly and efficiently on that cluster, right? So deep learning, if you want to scale out deep learning, you have to run it on a commodity server, a commodity cluster anyway. And in deep learning recently, there are two main techniques that you can use to parallelize our training. First one is data parallelism, where you just split the data in small chunks and run the training in parallel. That's what Spark does. That's what Hadoop is supposed to do. If you run most of the machine learning or deep learning model on Spark on Hadoop, that's what they do. They do data parallelism. Okay, but there's another technique that can be used to speed up deep learning training is model parallelism. If when the model is too big to fit into the memory, then of course you can either buy more memory, or you can just split the model in different server, and then you hope the training would get faster. In some case, we do observe that the training does get faster, but at the cost of coordinating between the different partitions of the model in different nodes. And so the trade-off between the data and model parallelism is not new. I mean, the database communities, they have worked on this problem for very long time. And what they conclude is, not to everyone's surprise, is that there's no one-size-fits-all solution. In some case, that you can sacrifice the correctness for speed, but in some other case, you cannot do that. Right? So this is the first problem that distributed deep learning has to address, and I believe that they can benefit a lot from what the database community have worked on in the past. Okay, so the second problem is a communication bottleneck. This is a corollaries of what happened when you try to distribute the model, or you distribute the data onto multi-nodes. Not all the problems are embarrassingly parallel. So not all the problem can be run directly on Hadoop or on Spark. So those problems that cannot be run on that manner, they have to communicate. I mean, the server have to communicate with each other, and then when they need to communicate, then the communication will become the bottleneck. Right? So most of the work in the deep learning space these days, they focus on actually improving the communication efficiency in order to avoid the bottleneck. Right? So one way they did it is to decentralize the architecture called parameter servers. So instead of having one centralized server that stores the model, they would distribute that centralized server in the P2P manners, or in the tree structure, and that would reduce the communication between two nodes in the network. And the other technique they can do is compression, or they can do hybrid parallelism, or they can use latest hardware like RDMA or InfiniBand network to speed up the network or increase the throughput of the network. But again, all of those techniques are not new. I mean, the database community, they have to distribute the SQL server, they have to distribute the key value workload, they have to distribute the transaction workload over many nodes, and they run into the same problems. So, I mean, again, I think the deep learning community can benefit a lot from what the technique that database community have come up with. Okay, another problem that is common between two communities is the consistency model. In database, people talking about very strong consistency, they talk about the transactional consistency. So I don't want to delve into more detail here, but very strong consistency system are the one like MySQL or Redis. So the one that I just found out today that they actually provide very strong consistency model as well. And the system that at the other end that provide weak consistency is something like Cassandra. Okay, so so consistency model is just one manifestation of the distribution of the model onto multiple nodes, of making the trade-off between the correctness of the computation and the speed of the computation. So if you choose very strong consistency model, then the model would run very slow. But if you choose to tolerate some correctness, some incorrectness in the model, then yes, then you can speed up the model and hope for the best. And you hope that even though it's incorrectness it is incorrect in every single step, but eventually you can train very fast and you can get to very accurate model as well. Okay, so the last common theme is on memory management, and even though memory has become cheap and faster, but it still is a scarce resources, and you cannot entirely replace RAM with you cannot entirely replace this with RAM yet. So so in the database community, they have worked a lot on how to share the memory between many nodes. They work on the virtual memory management techniques, and they work on garbage collection techniques, try to make the best use of all the RAM available on the clusters. Okay? And the same thing is happening in the deep learning community, even though it's not the big focus, because most of the deep learning platforms this day are developed by big players like Google or Facebook, and they have enough money, they have enough resources to pull a lot of RAM together. So the model would never be big enough to require this memory management. So I mean, so if you are big players like them, then you don't need to worry much about the memory management. But if you have constrained resource, if you were to run the model on a commodity cluster, then this is the thing you have to worry about. So this is a quick recap of some of these techniques that different open source systems nowadays. Those are very popular open source systems that we have seen, and how they are compared across different metric, different techniques that they use. So you can see TensorFlow is here as well. Even though it's very new, but it's basically used many of the techniques that have been used in the database community. And so you can see here that there's not single system that utilize the best, that use all of this technique in the best way possible. Right? So there's still room for development. There's still room for improvement here. Okay, so the next one is just I only have one slide on this because deep learning is quite new and it's just starting to find application on the database space. So first thing that you can use deep learning for is to do a human query interface to replace SQL. Okay, and for example, you can use RNN to replace it, to pass the language into SQL. And the second application is you can use something like auto encoder to extract the structure from a lot of text, and from that you can implement the data and knowledge fusion application. So you can construct a knowledge graph and you can construct the entity relation from using many of those deep learning models. Okay, so my last set of slides would be just a quick introduction for, I think Singa has not been very well very well known across the community. So I like to just to have a brief introduction of what we do here. So Singa is actually a Apache incubator project that has been in the incubator for more than a year, and we have released a third version that supports distributed training on single node and on multi-node as well, and over multi-GPU. And we support a lot of hybrid parallelism techniques, and we have Python binding, even though the core is developing in C++. And our main abstraction is a layer abstraction, which is actually a higher layer than what TensorFlow and TNOs or Torch they expose. So this is an early comparison. Long time ago, I think only the first month after TensorFlow has came out, and because many of you might have known that when it first came out, TensorFlow has not been fully optimized, and the performance of it is not very good. But so we also compare with MXNet, with Torch and Caffe as well, and Singa is, you can see, at least comparable to all of those state-of-the-art as well, and we can scale to 128 nodes on a single cluster. So we are releasing the next version 1.0, which and we're going to incorporate a lot of low-level optimization, both for speed and for memory. And we expose a lower abstraction, which is the tensor abstractions. Okay, I will not go into detail here. So this table that summarizes some of the features that we plan to incorporate into the next version. So basically, Singa will expose an imperative programming model as opposed to declarative one, like in TensorFlow or in MXNet or CNTK or Thino. So the imperative programming model make it easy for user to debug. And it's also run cross-platform. It's supposed to incorporate many of the techniques that we got from the database community. Okay, and this is a thing that we develop on the side as well. We try to make deep learning as a service. We try to develop something that can run seamlessly on the cloud, where the users can go in and then configure their model to some GUI, and then configure how many nodes it's supposed to run, and that's it. It's go off and run. Okay, so in conclusion, database techniques have a lot to offer to the deep learning community. Like they can offer a lot of optimization technique, like execution plan, memory management, etc. And also deep learning is also very useful for the database applications. So query interface, knowledge fusion, and data analytics. And finally, please check out our project. It's available online. It's supposed to be very usable, extensible, and efficient. And it has been used for the internal healthcare analytics, product search, and malware detection in-house as well. Okay, thank you very much. Thanks.